Alright, so this time we're going to be taking a look at section 11.3, which deals with Pythagorean theorem, distance formula, and circles. Now, the Pythagorean theorem has to do with a relationship between the lengths of the sides of what's called a right triangle. And so with our right triangle, what makes it a right triangle is the fact that we have a right angle, which is a 90-degree angle here. So these two sides that help form that right angle are called legs. So this is one leg, and this is another leg. And the side that's across from the right angle is what's referred to as the hypotenuse. So once again, the two legs that make up the right angle, the hypotenuse is the side that's across from that right angle. So if we were to take a look at the lengths of the sides of this right triangle, we might call the length of this leg A, maybe the length of this leg is B, and then the length of the hypotenuse is C. Well, what the Pythagorean theorem tells us is that if A and B are the lengths of the legs and C is the length of the hypotenuse, then C squared is the same thing as A squared plus B squared. That's our Pythagorean theorem. So go ahead and more formally put it up here. And so once again, if we have A and B are the lengths of the legs of a right triangle, and C is the length of the hypotenuse, then C squared is equal to A squared plus B squared. Now, we can take a look at some examples in which we investigate the lengths of the sides of a right triangle. So, in this example, we're looking at taking a look at the length of the third side. We'll be given two sides lengths, but we'll be figuring out what the length of the third side is. And so let's take a look at a couple of different examples. Might help to put those examples before the solution. So in part A, let's suppose that you have a picture that looks maybe a little bit like this. You'll have your right triangle sitting there, and let's say that this side has length 6 and this side has length 8. So what is the length of that third side? You could have another situation in which maybe you have a right triangle oriented that way. Maybe this side has length 5, maybe this side has length 13, and we're wanting to try to figure out the length of that third side yet again. Both of these examples are examples of right triangles. And so when we go to take a look at the solution for part A, let's think about the fact that the two sides whose lengths are known are the two legs of the right triangle. And so if we take a look at maybe this is 6 and this is 8, we could say, well, A is equal to 6, B is the same thing as A, so what is C? Well, according to the Pythagorean theorem, C squared equals A squared plus B squared. So we can go ahead and write that out. So C squared will be the same thing as A squared. Well, A is 6, so you'll have 6 squared. Plus B squared, well, B is 8, so you have plus 8 squared. 6 squared, same thing as 36. 8 squared, Same thing as 64. 36 plus 64 gives you 100. Well, if you want c, then take the square root of 100. Square root of 100 is 10. And so the length of that hypotenuse is 10. Now we can do something similar with the other part here. We have another right triangle. So for this right triangle, we have this side has length 5. We don't know the length of this side, but this side has length 13. When we observe this triangle, however, we notice that this side, whose length is 5, is a leg of the right triangle. This side, whose length 13, however, is the hypotenuse. So it's the length of one of the legs that we're missing right now. And so I could label this side as B if I want, and I think I do. Label this side as A, so A will be 5, and then label this side with C, so C is 13. Again, we have C squared is equal to A squared plus B squared. But this time we have C equals 13, so that left side is going to be 13 squared. We have A is 5, so we'll have on the right side 5 squared plus B squared. So 13 squared, same thing as 169. 5 squared is 25. And so we have 169 is the same thing as 25 plus b squared. Now if we subtract 25 from both sides of this equation, the 25 will go away on the right side, but 169 minus 25 gives us 144. So we get 144 is equal to b squared. And in order to get b, we would simply take the square root of 144, and that gives us 12. So b is equal to 12 in this case. So we have basically essentially a situation in which we were given the lengths of two legs. We had to figure out the length of hypotenuse in part A. And in part B, we were given the length of one of the legs and the length of hypotenuse. We had to figure out the length of the other leg. So you might say, well, how is this useful? Well, one possibility is illustrated in the next example. And so in this next example, let's say we want to find the distance in miles across some sort of lake from some point A to some point B. Now, we're going to have some sort of figure that we're going to draw for that, but the goal is going to be to find the distance. And let's suppose that the lake is going to look something like this. And maybe we have our point B here, maybe we have our point A here. And it's this distance across that we're going to want to find. Now perhaps we know a little bit more information. So let's take a look at this distance here. That's what we're trying to figure out. So that's the distance we want. But maybe we know that the distance from point B to this location is 4.4 miles. And maybe the distance from this point to that one is something like 5.3 miles. And let's suppose we have a right angle between this side and this side. Well, now we have a right triangle where one of the legs has length 4.4 miles, the hypotenuse has length 5.3 miles, and what we're trying to do is figure out what is this length of this leg, which is the distance that's across the lake. So we consider Pythagorean theorem yet again. think I'd like to redraw the triangle. And the distances that I'm going to have along here are in miles. So we have 5.3 miles as the length of the hypotenuse, 4.4 miles as the length of this leg. And suppose we want to call that length B. Well, then I would say that A is the same thing as 4.4. And I would say C is the same thing as 5.3. Now, according to Pythagorean theorem, C squared equals A squared plus B squared. So we would have 5.3 plugged in for C. So 5.3 raised to the second power on the left side. We would have 4.4 plugged in for A. So on the right side, we would have a 4.4 raised to the second power plus B squared. Now, the 5.3 raised to the second power is going to give you 28.09. And the 4.4 raised to the second power is going to give you 19.36. So we're going to be able to figure out B squared shortly. What we have to do is subtract 19.36 from each side of this equation. And when we subtract 19.36 from each side of the equation, we get a left side is equal to 8.73. So 8.73 is the same thing as B squared. To get B, you would need to take the square root of 8.73. And if you take the square root of 8.73 and round it, you'll get that the lake is approximately 3 miles long, or 3 miles across. All right, so we've taken a look at several different examples using the Pythagorean theorem. The next part involves the distance formula. So you might ask, well, how do we find the distance between 2 points? Well, we did a little bit of that right here, it turns out. But the distance formula in general is actually going to be based upon the Pythagorean theorem. So what I'd like to do here is think about what would happen in a particular example where we have a graph. And let's put some marks on the graph. So we have our y-axis here. And we have our x-axis here. And what I'd like to do is put a point here, maybe at 1, 2. And I think my other point I'm going to put here at 5, 5. So we'll have 1, 2, and then we'll have 5, 5. My goal is to figure out the distance between these 2 points in the plane. Well, one strategy that we could have is to draw a line segment between these 2 points. And if we draw a line segment between those 2 points, we might say, well, there's a certain distance horizontally and there's a certain distance vertically that we ended up having to move to get from this point to that one. So let's consider the horizontal distance for a moment. Well, to get from this point to that point, we had to move a distance from x equals 1 to x equals 5. That's 4 units. And to move vertically from this point to that point, y-wise, we had to move from y equals 2 to y equals 5. So what we've done is we've formed a right triangle. These are the legs, and this side that joins the 2 points, 1, 2 and 5, 5, is that's the hypotenuse. So if we were to label this side with D for distance, then we know that d squared is the same thing as 4 squared plus 3 squared. Now the 4 squared is the same thing as 16. The 3 squared is the same thing as 9, which means d squared is 25, or d equals 5. So now we know the distance between this point and that point is 5 units. But let's investigate this just a little bit more. Think about the distance of 4 that we got here. I said we had to move from x equals 1 to x equals 5, but if you look at 1 and 5, those are precisely the x-coordinates of the given points. So that distance that we have here is actually this x-coordinate minus this x-coordinate, 5 minus 1. 5 minus 1 certainly gives us 4. And the vertical distance that we had to move is 3 units. We got that from having to move y-wise from 2 to 5. Well, if we're moving y-wise from 2 to 5, that distance here is going to be the difference in the y-coordinates, so 5 minus 2. That 5 minus 2 gives us 3. Now, if you generalize this concept, then you can get the distance formula from the Pythagorean theorem. So the idea goes something like this. We'll have our x-axis, we'll have our y-axis, and we'll have a couple of different points here. So the same type of setup that we have in this illustration. It's just that I'm not going to assign coordinates like 1 and 2 here. I'm going to be a little bit more general. So we'll have, let's say, x1 and y1 as the coordinates for that point, and we'll have x2 and y2 for the coordinates for this point. And our goal is to figure out the distance between those 2 points. We're going to label that distance with d. Well, just like before, to get from this point to that point, there's a certain distance horizontally we have to move. There's also a certain distance vertically we have to move. So we'll take a look at the horizontal distance and take a look at the vertical distance, and now check it out. We've got this right triangle. But just like before, if we're trying to figure out the horizontal distance that we moved, we're taking the difference in the x-coordinates. Here, that 4 was given to us by 5 minus 1. But if we take the difference in the x-coordinates here, we're going to get x2 minus x1. So x2 minus x1 is the distance traveled horizontally as we move between these 2 points. But we also see a vertical distance that's been moved. And that vertical distance, in the previous example, was 3. But we were able to get that by taking the difference in the y-coordinates, so 5 minus 2. If we take the difference in the y-coordinates here, we have y2 minus y1. So y2 minus y1 is the vertical distance that we move to get from this point to that point. Now, we have a right triangle. The length of this leg is x2 minus x1. The length of this leg is y2 minus y1. The length of the hypotenuse is d. So according to the Pythagorean theorem, the square of the length of the hypotenuse, or d squared, is equal to the sum of the squares of the lengths of the legs. That is, we're going to have this length, x2 minus x1 squared, plus this length, y2 minus y1 squared. All right, so once again, that is our d squared. Now, if you want d, then what you're going to want to do is square both sides of, or sorry, take the square root of both sides of this equation. And that gives us our distance formula. We'll have d is the square root of x2 minus x1 squared plus y2 minus y1 squared. So once again, that is our distance formula. So we can take a look at certain type of example where we're trying to find the distance between two given points. And that'll be the example that I do next. So let's find the distance between the points. Let's go with -3, 4, and let's go with 5, 9. All right, we'll see how that works out. Sometimes when you find these distances, the answer is going to be kind of ugly. That's all right. It happens that way sometimes. But notice the distance formula. You've got two different points, x1, y1, and x2, y2 under consideration. So in a problem like this, what I would recommend is take one of the points labeled as x1, y1, and label the other one as x2, y2. Now it doesn't matter if I call this x1, y1 instead, and then call this x2, y2. I just want to make sure that I have consistency with the labels and that sort of thing, typical sort of thing going on. So what happens in this case is we get the following. So D is going to be the same thing as the square root of the square of x2 minus x1 plus square of y2 minus y1. So what we're going to do is we're going to plug in 5 for x2, and then we're going to plug in a -3 for x1. So that's going to give us 5 minus a -3. Now that'll get squared. And then we'll add y2 minus y1 squared. Here we have y2 is equal to 9. And then we have y1 is equal to 4. And when we take 5 minus a -3, that's the same thing as 5 plus 3, or 8. So D is going to be the square root of 8 squared plus, and then 9 minus 4 gives us 5. So we'll have 5 squared. And now 8 squared is the same thing as 64. 5 squared, same thing as 25. So underneath the radical, we now have 64 plus 25, same thing as 89, which means that the distance is equal to the square root of 89. All right, so the last part of this section deals with circles. And so you might say, well, what on earth do circles have to do with Pythagorean theorem or the distance formula? And the answer, a lot. So we'll take a look at the equation of a circle in this part. So a circle is going to have a certain center, and the circle is defined as the set of all points in the plane that are a fixed distance from a central point. So when we think about how to get the equation for a circle, well, let's start to draw this. And we'll have our center here. And we're going to assign some coordinates to that center. And a lot of times in different books, you'll see the letters H and K representing the center, the coordinates of the center of the circle. But what we're interested in is figuring out, well, what does an arbitrary point on the circle look like? And so we can sort of randomly pick some sort of point if we want to, maybe stop here. And this will just be some arbitrary point on the circle. And we're going to give it coordinates x and y. Now, one thing we have to keep in mind here is that no matter where we stopped on this circle, so if we had stopped here, or here, or here, or here, here, doesn't matter. If we take the distance from that point on the circle to the center, we're always going to get the same thing, always going to get the same constant. And that constant that we're going to get, the distance from the center to a point on the circle, is called the radius of the circle. And we're going to use the letter r to denote the length of that radius. And so you might think about how the distance formula might be relevant here. But r is the given distance. H comma k and x comma y are the given points. Okay, well, if we were to label, let's say, this point as x1, y1, and label this point as x2, y2, as we see here in the statement of the distance formula, then we'll just go ahead and apply that formula and see what happens. We can actually go back to this form, which is really what we're going to want to do. R is the distance, so that left side, distance squared, will be r squared. And that'll equal, you're going to have the square of x2 minus x1. Well, x2 here is x. We're going to subtract x1, which is h in this case. So the x2 minus x1 raised to the second power is going to be x minus h raised to the second power. We're going to add to that the square of y2 minus y1. y2 is y, y1 is k, so we finish out the right side with the square of y minus k. And this is an equation for a circle of radius r centered at the point h comma k. And so I want to take you through a couple of examples in which we consider what the equation for a particular circle would be with a certain center and radius. And then we can also go in the opposite direction and say, well, we know what the equation is, so what can we say about the radius and the center? So for the following example, we're going to be given some information about the circle, and then we're going to want to come up with an equation for that circle. Find an equation for the circle. With given center and radius. And I'll do a couple of these. So let's suppose that we start out with center at the origin. And then maybe the radius is going to be 5. Okay, so center is at the origin once again, and the radius is 5. Of course, we could also have center not at the origin. So maybe the center is at -2, 7. And maybe the radius is square root of 34. So in each one of these cases, we're going to come up with an equation for the circle, keeping in mind that the general equation for a circle of radius r, center h comma k, is given to us right here. Now, we could put the r squared on the left side or the right side, really doesn't matter. I think I'm going to rearrange things and just say, let's take the r squared, put it over to the right side. But if I do that, just keep in mind that given equation, x minus h squared plus y minus k squared is equal to r squared. So for part A, remember the center has coordinates h and k. This means that h is equal to 0 and k is equal to 0. Also, with the radius being 5, r is the radius, r is 5. So if we plug in these numbers to this general form, the equation, we'll have x minus 0 raised to the second power, plus y minus 0 raised to the second power, is equal to 5 to the second power. But x minus 0 is the same thing as x. So we're going to have x raised to the second power plus, and y minus 0 is y, so we'll have plus y raised to the second power. And then 5 squared, yeah, that's going to be 25. There's our equation. Looks pretty nice. Now, we can do the same thing for part B. If you take a look at part B, here you're going to have h. Remember, h is the first coordinate of the center, so h is -2. And we're going to have k is equal to 7. The radius is r, which in this case is the square root of 34. We go back to this general form for the equation, and we're going to plug in -2 for h, 7 for k, square root of 34 for r. Well, that means we have x minus a -2 raised to the second power plus y minus 7 raised to the second power is the same thing as the square root of 34 raised to the second power. Now, we're going to want to clean this up just a little bit. So, for example, the x minus a -2, same thing as x plus 2. So we'll have x plus 2 raised to the second power plus, and we'll have y minus 7 raised to the second power. Now on the right side, square root of 34 squared gives us 34. So it may not be quite as nice looking equation as we had before here, but full credit always looks nice. And that's what you would get for this answer for part B. Alright, so this example involved getting the equation if we know the center and if we know the radius. But what if we start here? Or what if we start here? Well, if we start with the equation, then we can figure out what the center of the circle is, and we can also figure out what the radius is. And that's what this last example is going to deal with. So here we're going to determine the center and radius of the circle. In the first case, we'll have x squared plus y squared is equal to 36. And the second case won't look quite as good, but let's say we'll have x minus 3 raised to the second power plus y plus 5 raised to the second power is equal to 81. So let's compare, in part A, this equation to what we're seeing here. Well, x squared is the same thing as x minus 0 squared, so that's going to mean that h is equal to 0. Now that's important for us because h is the first coordinate of the center of the circle. So let's go ahead and write that down. We have h is equal to 0. And then we're going to have y squared. Y squared, compare it to y minus k squared. Well, it's going to match up if k is equal to 0. And then the 36 is the same thing as r squared. Well, if r squared is 36, take the square root of 36, you get r to be 6. So we're going to have h equals 0, k equals 0, r equals 6. That means that our center is at the origin, and the radius is equal to 6. Now, for part B, you have x minus 3 raised to the second power plus y plus 5 raised to the second power is equal to 81. So let's compare the x minus 3 squared to the x minus h squared. Now, h is actually the number being subtracted from x here. 3 is the number being subtracted from x here. So that means that h is equal to 3. Next, we compare the y plus 5 raised to the second power to the y minus k raised to the second power. So if you really want what's in the parentheses here to match up exactly with a y minus k form, then what you're going to want to do is think of this y plus 5 as y minus a negative 5. So y plus 5, same thing as y minus a negative 5 squared. So this definitely has a y minus some number squared format. Well, what happens is k is the number that's being subtracted from y here, and technically negative 5 is the number being subtracted from y here. That means that k is the same thing as negative 5. We also have r squared as 81. So it's the right side of this equation. R squared equals the right side of this equation, 81, which means that r is equal to 9. Square root of 81 is 9. Now remember, the center has coordinates h and k. So 3 comma negative 5 is what we get for the center. And then the radius is equal to 9. One thing you might notice is that when you have the standard form equation like this, if you switch the sign of the number here, negative 3 to positive 3, that's going to give you the first coordinate of the center. If you switch the sign here from positive 5 to negative 5, then it's giving you the second coordinate. And the reason for this is when you take a look at the standard form equation, this number is what's being subtracted from x. This number k is what's being subtracted from y. So here, positive 3 is being subtracted from x. Positive 3 has opposite sign of negative 3. And here, technically, negative 5 is being subtracted from y, and negative 5 has the opposite sign of the positive 5 here. So we see both directions with our circles, getting the equation for the circle if we know the center and radius, and then also determining the center and radius if we know the equation for the circle. So the recommended exercises from section 11.3 are going up shortly. So we'll have 1, 7, 9, 13, 15, 23, 27, 35, 39, 43, 45, and 49.